Hey guys, welcome back to another lecture video for Chem 115. In this lecture video, we are going to talk about our next thermodynamic quantity, and that is entropy. And so this word entropy has been loosely associated to this idea of disorder. And so I thought it would be fitting for me to draw like this cartoon image of like a very, very messy room to kind of highlight this idea of disorder that's associated with entropy. Hopefully by the end of this lecture video, you guys will understand why those two concepts are typically associated or linked to each other. So let's go ahead and start. Entropy, the first thing I do want to discuss about entropy is its symbol. And so we're going to abbreviate entropy using capital S. The reason why I point that out, I know it's super simple, but I have seen some students associate entropy with enthalpy, which is capital H. And that's something that you guys don't want to do on an exam. And if you guys look at the letters that make up entropy, there is no S. And so E is not entropy, En is not entropy, it's just simply capital S. So what is entropy? Entropy is nothing more than just like a numbers game. And so it's all about probability, the most likely outcome, and the list continues. So according to statistical mechanics, entropy is related to the number of microscopic configurations, also known as macrostates, that a system can have that's specified by some type of macroscopic variable. More commonly, it's known as a macrostate. And so before we continue on our discussion with entropy, let's take a brief moment to discuss this idea of microstates and macrostates. And so microstates is going to be abbreviated by the symbol omega. And whenever you guys are talking about a microstate of the system, you're talking about things that would describe each particle. And so, for example, like energy. And so what is the relative energy of one particle compared to another? You can also talk about the position of the particle with respect to another particle, or degrees of motion, degrees of freedom between two or more particles. And so degrees of motion would be things like translation, rotation, vibration. Okay? And so when you guys are talking about the microstates, you're talking about the individual particle and what it quote unquote looks like if we had on like our molecular goggles and all of that stuff. And so since we can't really see the individual microstates of each particle in a system, we have to talk about the macrostate. The macrostate is just a general description of the system, very similar to the first lecture video. We can go ahead and describe the macrostate as like using units such as like pressure, volume, or temperature, right? So you can say that this system, when it's at equilibrium, is 1 atmospheric pressure. And when you say 1 atmospheric pressure, that would describe the macrostate of that system. Now, how the microstates, how the micro configurations look like within that system, that's going to be described by the microstate. Okay. So simply put, another way to describe entropy is, entropy will give us an idea of the number of equivalent ways that energy can be distributed. And so when you guys are looking at the equivalent ways that energy can be distributed, you guys are referring to the individual microstates. And like what I mentioned earlier, entropy is more or less like a numbers game. It's focused on probability. And so the system overall tends to move towards the most probable outcome. And so it's not to say that it's impossible to achieve a specific microstate. It's just very, very highly unlikely. And so the last thing that I want to talk about, or the last point that I want to make about entropy, is that it's going to be used as a state function, where we're using this idea of entropy to describe the equilibrium state of a system. We're using the perspective of probability, whereas, enthalpy is describing the equilibrium state of a system through this idea of energy and heat. Okay. And so entropy is another state function. And if you were to take the difference of the entropy in the initial state and the entropy in the final state, you can get some idea of the thermodynamic process that occurs as the system goes from one equilibrium state to another. And so to demonstrate the idea of entropy as disorder and to really put a lot of these terminologies together, such as microstates and macrostates, we're going to go ahead and look at a few examples. And so here I've kind of pre-drawn some of these boxes just to kind of expedite the video. And so I want you guys to imagine that you have a container consisting of two gas molecules. What's the probability that they are equally distributed amongst the left and right side of this container? Okay. And so if you guys have two gas molecules, there's different ways that you guys can arrange those containers. And when we talk about these gas molecules are in motion, right? And so you're thinking that, so just imagine that you have these two gas molecules that's inside this container, and it's in constant motion. And what we're going to do is we're going to take, like a picture or like a snapshot of these two particles that are in motion, and then we're going to look at how how many different ways we can see different outcomes of these two gas molecules when we take pictures of them. So what do I mean by that? So let's just say that these gas molecules are in constant motion, and then all of a sudden we decided to click on our camera, and it turns out that both of those gas molecules are on one side, specifically the left side of the container. Okay. And so we would call this snapshot, this image, this picture, a microstate. Okay? Because this is the relative position of these two gas particles with respect to each other in this current microstate. They're both on the left side. Now, if we allow these two gas molecules to move once again, and then take another picture or a snapshot and see where they kind of land, well, another way that these two gas molecules can land, so to speak, when we take that picture, is that both of them are on each side of the box. Okay. And so we can have one molecule on the left and the other molecule on the right. And so once again, we allow these gas molecules to move around, and instead of, I'm just going to go ahead and temporarily just do this, just so you guys understand the point. So let's just say that this is gas molecule number 1, this is gas molecule number 2. This is gas molecule number 1, this is gas molecule number 2. So let's just say that we allow these molecules to move, and at some point in time, there's going to be a gas molecule. The gas molecule that's labeled 1 is going to be on the left, and the gas molecule that's labeled number 2 is going to be on the right. Okay? And so once again, these snapshots are representing different combinations, different possibilities, and where these two gas molecules can end up on either side of the box. And the last potential or possibility is when both of these gas molecules, 1 and 2, it's going to be on the other side, the right side of the box. And so when we're looking at these snapshots, if you will, of where these gas molecules could potentially end up on either side of the box, we see that if we see that there is one microstate in which both of the gas molecules are on the left side. And here we see down at the bottom that there's one microstate or one possibility in which both of those gas molecules are all on the right side. And so if we're taking a look at the middle, and if we kind of imagine that we're combining the two, because if I erase all these numbers, then what you guys see is two of the same thing. So these are equivalent microstates. Or equivalent configurations. And so here we have two microstates that describes both gas particles being on either side of the box. So we would say that here we would have a microstate of 2. And so these are all equivalent microstates, equivalent positions. And so the number of microstates kind of give us a clue on the probability. And so the probability for both of these gas molecules to be on either side of the box is 2 out of 4. And so here we can say that the probability of both these gas molecules found on the left side is 1 out of 4. And on the right side is going to be 1 out of 4. Okay. All right. So this example just kind of introduces this idea of the game, so to speak, the imagery that I'm trying to convey, as well as this idea of microstates. And so what we're going to do is we're going to increase the number of gas molecules and see what happens in terms of the number of microstates possible in the different combinations. And at some point it does get a little bit too lengthy. That's why I've kind of just like summarized it in one step, and you guys will see that in just a second. All right, and so if we have 4 gas molecules, what's the probability that they are equally distributed? Okay. And so I did already indicate the number of equivalent microstates down here on the right-hand side. And I'm not going to go through like the whole derivation on how I got that, but it's very similar to what I did here in the previous round. And so, for example, we can have gas molecule 1 and gas molecule 2, and they're both found on the left and left. And here we can have gas molecule 1 and gas molecule 2. One microconfiguration or microstate could be like left and right. And then here we can have gas molecule 1 and gas molecule 2, and this can be in the right and the left, right? So these are like the combinations that describe this microstate. Okay. And so this one right here is going to be like gas molecule 1 and gas molecule 2. They're both going to be found on the right and the right. And so once again, that combination is representative of this microstate. And so it turns out that there's only one equivalent way to depict all four gas molecules being on one side of the box. And so, for example, we can have all four, 1, 2, 3, 4 of these gas molecules found on the left side of the box. And there's only one equivalent way to express that. Like there's no other possibility, there's no other combination where if we have gas molecule 1, 2, 3, 4, if we start labeling this, they're all going to be on the left, 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 left. Okay? And so there's only one possible way to create this combination for all four of these gas molecules. And then we can go ahead and talk about the other extreme. So for example, if all the gas molecules are on the right, so we have 1, 2, 3, 4, then this is telling us that we only have one equivalent way to ensure that 1, 2, 3, 4, gas molecule 1, 2, 3, 4, they're all found on the right, 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 right. Okay. And so it turns out that there are four equivalent ways to distribute these atoms, or these gas molecules, sorry, such that there are 3 gas particles on the left and then 1 gas particle on the right. And so an example, just one example of an equivalent microstate, just to kind of demonstrate that point, 1, 2, 3, 4. So we can have one gas molecule number 1 being on the left, 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 and then we have the 4th gas molecule on the right. Or we can have gas molecule number 1, 2, 3, 4, in such a way that, gas molecule 1 and gas molecule 2 is on the left, but gas molecule 3 is on the right, and gas molecule 4 is on the left. Okay, so these are all equivalent microstates, all equivalent combinations. And if you go through the workings of that probability, you guys will get 4 equivalent expression, or 4 equivalent ways that demonstrates that 3 of those gas molecules is on the left, only 1 gas molecule is going to be on the right. Okay. And so this is where I got the 4. And so it turns out that there are 6 equivalent ways for me to produce the outcome such that 2 gas molecules are on the left and the other 2 gas molecules are on the right. So notice how I'm not labeling which gas molecule is gas molecule number 1, number 2, number 3, number 4. I'm just simply describing that there are 6 equivalent ways that will produce 2 gas molecules on the left and 2 gas molecules on the right. And so finally, I can go ahead and take one of these molecules and move it to the right. And it turns out that there are also 4 equivalent ways for me to come up with 3 gas molecules on the right and 1 gas molecule on the left. Okay. And so if we have 4 different gas molecules, we see an uneven distribution of microstates, such that it is more likely that this microstate is more likely to occur. Simply because it has more microstates. Okay. That means there are 6 different possibilities that will produce the same outcome, such that two gas molecules are on the left and two gas molecules are on the right. And so there is still a possibility, a higher possibility, that the distribution of the gas molecules is positioned such that three gas molecules are on the left and one gas molecule is on the right, or one gas molecule is on the left and three gas molecules are on the right. However, when we start looking at the extremes, notice how there's only one way to, one combination to express that all the gas molecules are either on the left or all gas molecules are either on the right. Okay. So hopefully that makes sense. And so what happens if we took a look at 10 gas molecules? And so there's no way for me, there's not enough time for me to derive every single one. But if you guys look at the results, once again, omega is representing the number of microstates. And the microstates in terms of probability, in this case is, what is the probability for all of those gas molecules to be on the left side? And so if you had to number all 10 gas molecules as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, what's a probability, or what's the different combinations that's available such that all 10 of them are on the left side or the right side? And, there's only one possibility that can be written out. And so if you guys are looking at the extremes, notice that there's only one microstate, or one way to express that all 10 gas molecules are either on the left or on the right. Now, if you guys are looking at the middle, actually there is no middle. So if you guys are looking at this diagram right here, notice that there are 252 equivalent ways to express, those 10 gas molecules being on either side of that container equally. So in other words, 5 on the left, 5 on the right. And so there are a good portion of, there's still a lot of micro configurations or microstates that describe the possibility, the probability that 6 of those gas molecules are either on the left or the right, and 4 of those gas molecules are on the opposite side of those 6 gas molecules. And so you can kind of see, if you were to plot this out, you kind of get this nice bell curve where we have this peak right here, and this peak is representing the microstate, the configuration that has the most microstates. And so in this case, if we have 10 gas molecules, we have a higher probability that if these molecules were kind of moving around inside the container, we'll have a higher probability that when we take a snapshot of it, it's going to be, half and half, right? And as we get closer towards the extreme, so for example, if these molecules are moving around the container, and if we take a snapshot of it, it's highly unlikely that we'll be able to take a snapshot or a picture such that all of the gas molecules are on one side or the other. Okay? So that's what this diagram is telling us, right? And so overall, these values in blue is representing the number of equivalent ways that that combination of these gas particles being distributed in the container is equal to. And so the idea that if you have a higher amount of microstates for that specific system, then it's more likely that that microstate will be sampled compared to a different microstate or a different configuration. All right, and so entropy can be described using this Boltzmann equation. So K is going to represent the Boltzmann constant. And W is going to represent the statistical parameter that describes the different number of microstates possible. And so if you were to take Boltzmann's constant and take the natural log of this statistical parameter that's describing the different microstates that's possible, then you get a value, and that number is going to describe entropy. Okay. And so why then is entropy considered or linked up or associated to this idea of disorder? And so that answer can be, or that question can be answered by looking at this diagram. And so here we have 10 particles. And these 10 particles are all kind of pushed off to one side of the box. And so we can go ahead and describe that since all of these particles are pushed in one side of the box, that they have very low entropy. And more or less these molecules are ordered, if you will. Okay. And so the smaller your volume, the order of those molecules is much higher, right? So you guys can kind of like, the analogy would be if you like lived in a closet like Harry Potter compared to like living in a very, very big room, right? If you guys are living in a closet, you definitely, things are set in certain places to make sure that there's enough room for you and your items. And so everything is kind of like compact and ordered, if you will. Whereas if you like live in a big room or a big house or whatnot, you can just like throw stuff around and it's not going to affect like your living area, so to speak. And so what would happen if I were to open this, this enclosure, right? If I were to erase that blue line, what's a probability for these 10 molecules to stay in one side of the box? In other words, the box that, the side that they were originally on. Well, I can go back and look at my derivation and I can say that there's, one chance in many that all 10 molecules will stay on one side of the box. And so, according to this idea of entropy, it is more likely that those 10 molecules will move around and occupy the entire volume of the container, such that such that if we took a snapshot of how those molecules are moving around, it's much more likely that they're going to be distributed evenly throughout that box. And so I'm just going to go ahead and create this box real quick. Okay. And so here we have a higher probability that all 10 of those gas particles are going to be spread more evenly throughout the box. And we're going from something that's very ordered, right? I'm going to go ahead and draw that enclosure again. So we're going from something that's very ordered to something to a place that's more disordered. In other words, higher entropy. And so you guys can think about this in terms of energy as well. It doesn't have to be like number of particles, number of gas particles. And so if all of your energy, if you will, is conformed to one specific section, and so if those molecules, let me retract. So you guys can go ahead and visualize this in terms of energy. So for example, if all of these little particles have some sort of energy to it, then the number of ways to kind of distribute that energy is very small compared to when you have a larger volume. Okay. I guess an analogy to this idea of ordered and disordered, just to kind of solidify the point, is you crouching underneath a desk. And so when you crouch underneath your desk, you can't really move or articulate your arms and your legs as much. And so your arms and your legs are kind of in this state of low entropy or order. However, as you kind of emerge from the bottom of your desk to, for example, the classroom, where there's this grand space where you can flail your arms, you can jump around, you can, shake your leg however you want. You have this, you increase the possibility for you to access different microstates. And so when you guys are talking about in terms of energy, you guys have a higher probability to distribute that energy when there's a greater volume in the system. Okay. So hopefully after going through this exercise, you get a stronger idea of what entropy is. Entropy, once again, it's a numbers game, right? What is the most likely outcome that will occur based on equivalent ways of expressing the microstates? All right. And so what we're going to do is we're going to look at the effects of macrostates on entropy, and we're going to go through some exercises to understand whether or not the system will be more ordered or more disordered, if it has a lower entropy, or will it have a higher entropy. And we kind of did volume already, but let's go ahead and do it again. And so, for example, if you guys have these molecules that are just on one side of the box, if you open the box, or in other words, increase the volume. So when you increase the volume of a container, whatever the container is, then you increase the entropy of the system. So it's moving towards like a microstate that has it's moving towards a state that has more equivalent ways of describing that specific microstate. And so if you decrease the volume of the container, I'll go ahead and do the opposite. Oops. Then your overall, the entropy will decrease. And so let's go ahead and talk about temperature. And so I want you guys to imagine that this box is representative of an ice cube. And so if we zoom in on a very specific part of the ice cube, here we can see the molecules, the water molecules, kind of stuck together, side by side. And so when you guys are going from a low temperature to a high temperature, entropy is going to increase. And so if you guys can imagine, when your ice cube is melting, all of the little circles that I've drawn, they're just going to, they're not going to be ordered anymore. They are going to sample, all of this volume, allowing an increase in the number of microstates that's possible. And that increase in microstate is what's going to increase the entropy of the system. And so conversely, if you go from a high temperature to low temperature, you're taking something that has, like a high degree of motion, high degree of freedom, to something that's very restrictive. And so entropy will decrease if you go from high temperature to low temperature. And so if you guys are thinking about this in terms of the statistical probability, then you decrease the probability of accessing different microstates. Okay. And so let's go ahead and talk about like physical states of matter. And this kind of goes back to the idea of like volume and temperature and all of that stuff, so phase transitions. And so when you guys are going from a solid to a liquid, a solid is very ordered, if you will, okay? Much like that ice cube. And so when you're going from something that's very ordered to something a little bit mobile, such as liquid state, so there's quote unquote more movement in the liquid state, because you have an increase in movement, then those particles can sample different microstates that was not available to them when they were in solid form, when they were like conformed or restricted to be in a specific position because they are solid in state. Okay. And so here there's quote unquote like less restriction. Okay. And so overall, when you guys are going from a transition from solid to liquid, then you guys are increasing the entropy of the system. You're allowing these molecules to sample more microstates. That's not possible in a solid crystal. Now, when you guys are going from liquid to gas, which of these two physical states of matter is more restrictive compared to the other? And so by just comparing these two items, liquid and gas, liquid in this perspective is more ordered than gas molecules. And so you guys can imagine that gas molecules are just like moving anywhere they like, they're rotating, they're vibrating, they have, they can access this extra degree of freedom that molecules in liquid state do not have the ability to access. And so when you guys are going from a liquid to a gas state, then you can go ahead and say that you're increasing the entropy of the system, right? So once again, this is going to be, so the gas state is much less restrictive than the liquid state in comparison. And so when you guys are going from solid to liquid, so this is like sublimation, you're going once again from an ordered system to something that's like less restrictive or more disorder. And so overall, once again, you're going to get an increase in entropy when you go from a solid state to a gas state. Now we can go ahead and quickly do the reverse. And so if you guys are going from liquid to solid, or gas to liquid, or gas to solid, then in all of these situations, what's going to happen is that you're going to decrease entropy. And so you're going from a very, disordered physical state of matter, or you're going from a physical state of matter that allows a higher degree of movement, and it allows those particles, those individual particles, to access different microstates. And you're going to a physical state of matter that's more ordered, which restricts those particles from accessing those those microstates that's available to those particles when they're in either liquid or gas state. All right, so let's go ahead and apply this concept for a few of these questions. So which of the following has the most entropy at standard conditions? And so these are the choices, A, B, C, and D. So here we see a liquid, something that's aqueous in state, and here we see something that's solid in state. And so we know that anything that's solid in state has low entropy, so we can go ahead and cancel these two choices out. And so that leaves us with the liquid state and the aqueous state. Now, if you guys have water that's liquid, it's just water. I mean, that's just it. But if you guys have, sodium chloride and it's aqueous in state, we know that that specific substance is soluble, and so it's going to separate to sodium ion and chloride ion. And so technically, you don't have one particle. You have two particles. And if you have two particles, that's more particles than this water molecule can produce in essence. And so these two particles can explore, can have more microstates or microconfiguration than one particle can have. Okay? And so therefore, letter B would be the answer to this question. So sodium chloride, that's aqueous in state, has a higher entropy at standard conditions, just because it breaks down to more particles. And since this is aqueous in state, we know that water is also present in the background, right? And so we have these different possible interactions with sodium ion and chloride ion, sodium ion to water, chloride ion to water, and the combination just kind of continues. All right. And so let's go ahead and talk about, predicting the entropy in a chemical reaction. And so typically you guys can do this by taking the difference in the number of moles of products from the number of moles of reactants. And so very similar to the other items, or very similar to the other stuff that we've done in previous lecture videos and previous lectures, the value for n is going to reflect the coefficient in a balanced chemical equation. And so the idea is that if you have a greater n value, if the number of particles is greater, then that means the system has greater entropy. So if you have more particles, you have more different combinations, more different ways to express the microstate of the system. And we should also remember that the physical state of matter, gas, has a higher entropy than liquid, than solid. Okay. So let's go ahead and take a look at this first example. So on the reactant side, we have 1 mole of nitrogen gas, and here we have 3 moles of hydrogen gas. And then after the chemical reaction occurred, we produce 2 moles of NH3. And so when, as you go from the reactants to the products, was there an increase or decrease in entropy? Okay. Well, the first thing that we're going to check is the physical state of matter. And notice that all of these are gas particles. And so we can go ahead and just look at the numbers and subtract them from each other. So products minus reactants. So here we have 2 minus 4, which equals to -2. And so if my n value is negative, then that tells me that I have a decrease in entropy as I go from reactants to products. Okay. So let's go ahead and take a look at the next example. So here we have calcium carbonate that's reacting with 2 moles of hydrogen ions, and that's going to produce calcium ion, water molecule, and carbon dioxide. And so here we're going to ask ourselves, what is the entropy of the system before and after the reaction? And so overall, will the entropy increase or will entropy decrease? And so here in this case, we're going to go ahead and check out the physical states of matter. We have solid, aqueous, liquid, and gas. So this is a situation where we have, a mixture of all of these different physical states of matter. But in this instance, what matters the most is that we have the production of a gas molecule. And so if we have the production of a gas molecule, then we know that the entropy is going to increase. And we can also apply this idea of number of moles of products and number of moles of reactants. So actually, let's do that first. And so if we look at the number of moles of reactants, here we have 1 and 2, so this gives us 3 moles of reactants. And so if we take a look at the coefficient for the products, we see once again 3 moles. And so if you guys are just comparing the number of moles between the reactants and products, they're the same. And so in terms of the number of particles, one can conclude that the entropy is neither increasing or decreasing as you go from reactants to products. However, what changes that scenario is the production of this gas molecule. And we know that the entropy of gas molecules is much higher than liquids, and it's also much higher than solids. And so if the difference in the number of moles doesn't work out and it's giving you the same number, then you might want to check your physical state of matter. And so overall, since we have the production of the gas, there is going to be an increase in entropy as we go from the reactants to the products. All right, so let's go ahead and take a look at this next example. So let's go ahead and look at the numbers first. So here we have 1, 1, and 1. So if you add both of these numbers, you get 2 moles of reactants. And so here we have 1 mole of reactant. And so we're going to go ahead and subtract both of them. So n is equal to 1 minus 2. And so in this case, we're going to have a value that's negative 1. Okay. And so looking at the physical states of matter, here we have aqueous, aqueous, liquid. But if you guys look at this substance hydroxide is not going to break down anymore. It's not like the example that we had at the very beginning where we had sodium chloride aqueous. If you guys have a cation and anion, then yeah, it is going to break down to produce more particles. But here for this example, hydroxide will not break down anymore. And so we can still treat this as just one substance. Same idea goes with this hydrogen ion. And so as we go from reactants to products, it looks like the physical states of matter are all equivalent. So we don't really need to pay attention to the physical states of matter since they're not going to change my answer. And since the value for n is minus 1, then this is telling me that as I go from my reactants to my products, I will decrease, or the system will have a decrease in entropy as we go from reactants to products. Okay. All right, so let's go ahead and look at this next example. Once again, we're going to go ahead and look at the numbers, look at the coefficients. And so here we have 1 and we have 1. And so if my n value is equal to 0, then that's telling me that I'm not going to increase or decrease the entropy of my system before and after the reaction. So there is no net increase, no net decrease in entropy as the reaction progresses from left to right. And so if that's the case, that's the scenario, the next thing that we need to check is the physical states of matter. And so if you look, here we have carbon dioxide that's in solid state. So we know that all of those gas molecules, all of those carbon dioxide molecules are going to be like lined up right next to each other. They're such that it's going to be very stiff, there's very low movement, they can't really explore any other microstates, any more microstates other than what's allowed for them in that solid state. When you guys look at the product, carbon dioxide, in gaseous form, now you have this different physical state of matter where all these carbon dioxide molecules are kind of zooming by and just roaming around, and they have this ability to access these different microstates that was not possible when they were constrained and restricted to a specific orientation because their physical state of matter is solid. And so because we have a difference in physical states of matter, and we know that gas has a higher entropy than solid, then we're going to say that overall our chemical reaction is going to increase in entropy. Okay. All right, so I think we have a couple more. All right, so here, same situation. We have the same molecule. And if you guys are looking at their coefficients, it's 1 and 1. So if we subtract those two, the value of n is equal to 0. And so preliminarily, this value of 0 is telling us that perhaps as we go from reactants to products, there is no net change in entropy of the system. However, if you guys are looking at the physical states of matter, here we have gas, here we have liquid. We're going from something that's very disordered, right? These gas particles are just moving around every which way, accessing all of these different microstates, to a liquid state, which is, it's still fluid, but there's definitely some constraint in the movement of those particles with respect to each other. And so as we're going from a gaseous state to a liquid state, we know that overall there's going to be a decrease in entropy. All right, so looking at this, I think this is the last example. Here we have 2 moles of aluminum, 3 moles of bromine, and 2 moles of aluminum bromide. And so if we're looking at the numbers specifically, so we have 2 moles of products, and we're going to subtract that from 2 plus 3, which is 5. So what we get is -3. So by subtracting the sum of the coefficients, already it's telling us that there might be a decrease in entropy as we go from the reactants to the products. And so the last thing that you want to do is you want to check the physical states of matter. So here it's solid, liquid, solid. And so between these 2 options, we know that liquid has a higher entropy than solid. And if you look, notice that liquid is going to be in the reactant side. And in the product side, we just have a crystalline solid. And so overall, we're going from a liquid state to a solid state. So that gives us a stronger idea that the entropy of the system is going to decrease as we go from the reactants to the products. And so here we have 2 conformations, is basically what I'm saying, that leads us to the same conclusion, that overall we have a decrease in entropy as we go from the reactants to the products. Okay. All right, and so hopefully this lecture video gave you a stronger idea of what entropy is and how we can use entropy or how we can use chemical equations, the coefficients, and the physical state of matter to predict qualitatively predict the change in entropy as we go from reactants to products. Okay, and so in the next video, we're going to learn how to start expressing entropy in terms of an actual value. All right, catch you guys in the next lecture video. Bye.